Quite amazing. It's remarkably exactly the right distance for Jupiter's gravity to dominate when 3 Atlas comes closest to it. And in fact, the non-gravitational acceleration that was reported after it came closest to the Sun, there was some push that was noticed in its trajectory, some slight deviation from the original path is needed in order to bring it exactly to that location. So by now I have even more puzzles, and the fact that NASA ignores the anomalies that 3 Atlas had, meaning the very small likelihood that it lies in the plane of the planets around the Sun, and its very large size, 1,000,000 times more massive object than the first interstellar object.
In an extraordinary turn of events, orbital data now indicate that 3I Atlas executed a precise adjustment in its trajectory, a 1 in a billion maneuver that brought its path to the exact outer edge of Jupiter's gravitational sphere of influence. Analysis shows the object experienced a non-gravitational acceleration near perihelion, consistent with outgassing jets or another subtle propulsive force. This adjustment shifted its closest approach so that it aligns almost perfectly with the Jupiter Hill radius, the zone where Jupiter's gravity overtakes that of the Sun. Without this exact change in course, 3I Atlas would have missed that boundary entirely. The magnitude of the shift corresponds precisely to what was required to reach that threshold. Viewed from a distance of hundreds of millions of kilometers, the result is striking. A natural visitor redirected with pinpoint accuracy to a target zone in our solar system. The finding adds a compelling piece to the puzzle of 3I Atlas's origins and behavior, demonstrating how even small forces can have extraordinary navigational consequences. As 3I Atlas continues its journey through the solar system, the timing of this course adjustment makes the finding especially compelling. The event occurred while the object was behind the Sun from Earth's vantage point, invisible to telescopes and unobservable by direct imaging. When it re-emerged and astronomers updated its trajectory, the result was a path that could not be explained by gravity alone. The acceleration was small, yet its consequence was enormous, a refined intercept with the outermost limit of Jupiter's gravitational influence. The Hill radius is not a place one accidentally strikes with such precision. It represents a delicate balance point, a liminal region where Jupiter's grip on orbiting material becomes just strong enough to win over the Sun's. Reaching that boundary requires an object to approach Jupiter at exactly the right distance, neither too close nor too far, moving with just the right speed. It is the kind of target that, if described as a bullseye, would be an understatement. In cosmic terms, even a slight deviation in trajectory would send the object drifting harmlessly past, never experiencing a change in gravitational allegiance. Yet here is 3I Atlas on track to approach that line within a fraction of a percent of precision. The statistical odds of such a match occurring through random physical processes are exceedingly small. Small jets of vaporizing ice do occur on comets. This is not unusual. What is unusual is for those jets to produce a net acceleration so perfectly matched to a long-term, distant orbital consequence. With hundreds of millions of kilometers between the object and its eventual rendezvous near Jupiter, the proverbial dart hit its mark long before the board came into view. Because the adjustment happened behind the Sun, the forces responsible cannot yet be studied directly. Some have suggested that the detected acceleration could be explained by sublimation of volatile ice, a mechanism observed in 2I Borisov and many long-period comets of solar system origin. Indeed, post-perihelion images of 3I Atlas reveal multiple outgassing jets contributing to its visible coma structure. These jets can introduce thrust, natural propulsion generated as sunlight heats and vaporizes frozen materials embedded just beneath the surface. On most comets, the resulting force is minor, altering the orbit only slightly. In extremely rare cases, the thrust can be enough to shift a trajectory by a significant margin.
But even among those rare cases, the level of accuracy achieved here stands apart. The shift was not merely significant. It was of precisely the magnitude needed to drive 3I Atlas to the exact circumference of Jupiter's Hill sphere. This is like flicking a grain of dust at the edge of a massive whirlpool from hundreds of meters away, only to have the grain brush that boundary within a millimeter. The gravitational dynamics involved span astronomical units and rely on initial conditions that must align with extraordinary accuracy to produce the observed outcome. As 3I Atlas proceeds toward Jupiter, the object will encounter a region of space where gravitational interactions shift from Sun-dominated to Jupiter-dominated. Any smaller fragments or debris accompanying it could find themselves captured, however briefly, within Jupiter's gravitational domain. If observations are correct, the close approach will occur in mid-March 2026, when the object passes the outskirts of the giant planet's influence before continuing its escape back into interstellar space. Its velocity at that time will far exceed Jupiter's escape velocity at the boundary, meaning the object itself is unlikely to be captured. Instead, the passage will be what dynamicists call a flyby at the edge, a near miss with gravitational consequences not yet fully understood. This raises a compelling question. What significance does this threshold hold for a natural object? In the realm of astrophysics, Jupiter's Hill radius is not typically a target of scientific interest for comets or asteroids. It is not a location that triggers a transformation like tidal disruption or thermal activation. There is no conventional expectation that such an object would benefit structurally or dynamically from passing near this gravitational threshold. Known natural mechanisms, resonant interactions, scattering events, volatile emission processes, do not preferentially aim for the Hill radius. Instead, the finding serves as a reminder that interstellar objects may not behave like familiar members of the solar system population. 3I Atlas is believed to originate from outside our planetary system, possibly ejected from a distant stellar nursery billions of years ago. Its composition, thermal history, and physical structure remain largely unknown. Laboratory studies of cometary dynamics suggest that small sublimation-driven accelerations can produce outcomes that appear targeted when viewed in hindsight, a product of chaos magnified over astronomical distances. Future analysis must determine whether that explanation adequately accounts for the precision observed here. Researchers are examining two broad interpretive paths. The first assumes that natural processes alone are responsible, that the observed acceleration is simply a product of asymmetric outgassing, and that the precise outcome represents a rare coincidence made possible by chaotic orbital evolution. In this view, 3I Atlas remains a comet, behaving within the realm of known physics, albeit with exceptional timing and results. The second interpretation is more speculative, yet cannot be dismissed without evidence. It considers the possibility that the acceleration was not merely the byproduct of sublimation, but a purposeful redirection produced by forces or mechanisms beyond typical cometary behavior. This does not imply artificial origin. A wide spectrum of natural processes remain poorly understood, especially those involving interstellar material and unknown volatile compositions. However, the door remains open to the unexpected. Interstellar objects represent new territory in planetary science, and extraordinary claims cannot be definitively ruled out when the underlying data reveal an extraordinary outcome.
Regardless of the cause, the precision of this maneuver presents a unique scientific opportunity. Jupiter's Hill sphere is enormous, a region more than 53 million kilometers in radius, yet it remains one of the least explored gravitational environments in the solar system. While spacecraft like Galileo and Juno have studied Jupiter and its moons up close, the outskirts of the planet's gravitational reach are comparatively uncharted. An interstellar object passing through this zone provides a chance to observe how a body from beyond the Sun's influence interacts with a giant planet's extended domain. Astronomers are now refining observation strategies to collect as much data as possible during the 2026 flyby. Precise tracking will be essential to detect any secondary acceleration events, especially if new outgassing occurs as 3I Atlas responds to Jupiter's growing gravitational pull. The Hubble Space Telescope, large ground-based facilities, and future wide-field observatories could all contribute to monitoring the encounter. Mission planners have even discussed the potential for serendipitous spacecraft observations,
Instruments aboard Juno, for example, could be tasked with looking outward rather than inward if mission constraints allow. What makes this encounter so compelling is the possibility that something measurable might occur within the Hill radius. Even a minute deflection, a faint dust trail, or a transient brightening of the coma could offer clues about how interstellar objects respond to the gravitational fields of massive planets. If fragments split from the main body, their fate could reveal the energy balance between Jupiter's pull and the object's high-speed escape trajectory. Should any material linger, however briefly, it may provide the first chance to study interstellar debris temporarily interacting with a planetary system beyond the Sun's immediate grip. At the same time, the flyby underscores how little is known about the population of objects wandering between stars. Interstellar comets may be far more common than the handful we have detected so far. If so, many may be passing through the solar system undetected, their low brightness keeping them hidden from surveys until they are too far away to study meaningfully. 3I Atlas reminds us that even a single discovery can reshape our expectations, prompting new theories about the formation, ejection, and evolution of material in planetary systems across the galaxy. The discovery also encourages expanded public interest in interstellar science. When objects like this appear and reveal unexpected characteristics, they challenge assumptions about Earth's isolation and invite curiosity about what else may traverse the space between stars. Humans have long wondered whether visitors from beyond our sun could carry information about distant worlds. In a strictly scientific sense, every interstellar object already does. Each preserves a physical record of chemistry and environment we cannot replicate on Earth. Whether natural or otherwise, 3I Atlas carries with it a history far older than our solar system. As scientists gather additional data, the interpretation of its behavior will continue to evolve. The next 2 years will be devoted to refining predictions of the Jupiter encounter, characterizing the non-gravitational forces at work, and searching for clues into the object's composition. The period following the flyby will be especially important. Any measurable deviations from expected behavior could reveal previously unknown processes. In the absence of further surprises, the event may ultimately be classified as an exceptionally rare but natural coincidence in the physics of interstellar comets.